our learning intentions. We will be learning about the different logic gates and how to draw the circuit symbols and fill up the truth tables. Your success criteria. You will be successful if you are able to differentiate the 6 logic gates and their truth tables. This is kind of a minuscule way of understanding each and every decision which is made inside a computer. As you know, that computers are digital devices. They use digits inside their brain for thinking and understanding, and they understand or speak only the language of zeros and ones, which are binary numbers. So let's look at how the zeros are changed to ones or ones are changed to zeros. That's basically how a switch works. When the switch of your light is turned off at your house, it's a 0, and when you switch it on, you are making the decision of 1 and you get the output there as a light. Similarly, there are billions of decisions being made inside a computer at 1 second. So we'll just take a look at how the decisions are influenced inside a computer. There are a lot of minute devices like transistors, resistors, capacitors, inductors that work inside a processor to help in this switching or decision making, as we can say it. There will be lots of zeros and ones, which are the inputs, and we'll see how the computer decides what to give as output when there is a specific combination of 0 and 1. So these are governed by the logic circuits. The logic definitely means thinking, so these circuits think and give outputs, and it's called as a logic gate as well, because gate is something which allows passage, not for everything. It has a certain criteria. For example, your school gate, it will not allow just anyone to get inside or anyone to go outside. There are specific conditions when the gate is opened and allow specific passage. So that's another type of logic gate that has its own working principle. We're going to learn how this switch inside the computer works, and for that we'll be learning how to make the truth tables. Truth tables are basically a tabular form that records the different inputs that we give to the logic gate and what output we get out of it. So it's kind of like testing, that if I give this, what will I get, or if I were to get this, what should I give. And we'll just look about the different logic gates and their circuit symbols, how to draw them. I'm not very good at drawing, but I'll try to show you how to draw it, so that if I were to show you a picture from a slideshow presentation or from one of your past papers, you'll be able to draw it on your own without like thinking, hey, how am I going to draw it? Because yeah, we'll just get there. There are 6 different logic circuit symbols that we use to define most of the decisions, and 3 of them are basic: and, or, not. Simple English vocabulary. It's having the same meaning with the word and or and not. The word and is used in between combining 2 words, like for example, I and my friend came to the school at the same time. So the statement defines that I reached the school at the same time, my friend reached the school at the same time. So it could be like another, the or can be used like, we could go for coffee at 3 or at 4. So it's like there is a possibility that you could go at 3 as well as at 4, not at both. You don't have a definite decision, you don't have a single choice output, but you have a combination of outputs. Just keep this in mind. I'll show you this, how it goes in the truth table, then probably you'll be able to understand it. And NOT is what you do other than supposed to be done. Like, you ask your friend to come to school with your pen, and he does not come to class with your pen. So think of it that way, and we're going to check these three statements in the diagrams, and probably you'll be able to understand what I'm trying to say with these statements. And those are the first three. The next three is NAND, NOR, and XOR. NAND comes with the AND in the end, and there is an N in the beginning, so its N starts for the NOT. NOT AND is NAND, NOT OR is NOR, and exclusively OR is XOR. And these are the next three gates. The first three gates are the basic gates, and the next three gates are the derived gates. Although it's not a standard definition to be used, like the first three gates are there. Like, you don't have to depend on any other thing to make those gates, but for the next three gates you have to use the first three gates. So that's why they are the derived gates. I'll try to draw this and learn how to fill up the truth tables, and then let's see. Alright, let's look at how to draw the different circuit symbols. We have 6 logic gates, so I'm going to take a paper and I'm going to write it into different parts. Like, there's AND, there's OR, there's NOT, and then comes the next part, NAND, there is NOR, and XOR. It's not XOR, it's XOR. That would be the way to pronounce it. I mean, that's the way I would love to pronounce it, because it gives me the idea that it is exclusively OR. It has the connection with the OR gate. The NAND and NOR are connected with NOT AND and NOT OR. So let's look at the AND gate and just have the circuit symbol. Okay, the AND is having the D symbol, so I'm just going to start with that. And it's a 2 input 1 output gate. I'm just going to give it as A, B, and let's go with Z, right? And the OR is somehow reminds of the R shape, R and the heart. So let's think of it like a heart. It's probably easy to draw that way if you think that it's shaped like a heart, and the R, and that kind of brings into your mind about this word. So this will be a Y will be the output, and I'm going to give it a C and a D. C, D are input, and Y. And then NOT is supposed to be a single input, single output gate. It's an inverter gate, so we'll just single input and single output. If it's the NOT, just remember of this KNOT, NOT. So that is there, and then the somehow remembers of the NO and the T somehow. So this is how I remember the different gates. You might find it useful, or you can devise your own method. So I'm going to give this output as X, and then this is going to be an E. Okay, so next is the NAND. NAND is obviously having the AND part. It is NOT AND. Alright, so we're going to use the NOT. The KNOT is referred by this O, the small o. So it's basically the AND gate, that's shape of the AN and a D shape with the circle on the tip. So this is how the NAND gate looks. Sequentially we're going to give it as the names, like E comes F and G, so Z, Y, X. So yeah, and then goes for the NOR. NOR is also not OR, and it's the same OR gate symbol with the NOT at the edge of the output. So here it will be H and I, and here is the V. Okay, so the XOR or the exclusive OR, so we're going to use this space, and it's also having the OR part. So the output is going that way. There's another line here that selectively chooses specific input to be considered for the OR gate. So that's J and K goes for U. So I'm using different letters for this so that each input and each output can be evaluated accordingly. Now let's look at the truth tables. As we know, the truth tables are a record of how the input is given to the specific gate and how the output is affected. It's like a record of how like specific input is changed into a specific output. So in that, A and B are the inputs and we have Z as the output. Okay, so it's the basic of binary numbers. We try it like this. We go with 0, 1, 2, 3, 4, 5, 6, 7, 8. Just like how you start counting, except that you start from 0 here. So 0 in binary is obviously 0, and 1 is 0, 1, 2 is 1, 0, 3 is 1, 1. When it goes to 4, it becomes 3 digits, becomes 1, 0, 0. 5 is 1, 0, 1. 6 is 1, 1, 0. 7 is 1, 1, 1. And for 8, we go for the 4 digit. It's 1, 3, 0, 0. So for any logic gate with n number of inputs, we have 2 to the power n number of outputs. So here we are having these logic gates with 2 inputs, right? So the output will be obviously 2 to the power 2, it goes 4, and 4 outputs are calculated with these set of values. So that's why we're going to use these 4 in the input section. It goes like 0, 0, 0, 1, 1, 0, 1, 1. Different combinations of input from A and B. Now in an AND gate, it specifically said that the word AND. Imagine the condition that, let's give it an example, like this is your house, okay? A house, getting inside the house is a Z, the door is a B, and you have an outside gate with the door of A. Imagine the situation that you are coming to the house. All right, I'm not very good at drawing, but still, just say that this is you. You're coming to the house, and in case if you want to go inside the house, that is the Z is going inside the house. All right, so A is your outside gate and a B is your door. Imagine that you don't have the gate key and you don't have the house key. Will you be able to go inside the house? I don't think so. And one day you come without the gates key, but you have inside key. Just let's say that you are not able to jump over this fence and go there. Like, you're a legit person who will not do anything bad like jumping and destroying this wall. So in that case, you had the house key but you don't have this gate key, so you'll not be jumping it, so obviously you're not going inside. In the another case that you have the gate key but you forgot the house key, obviously you'll not be able to break the door inside, you're not going there. And the last case where you have the key to this gate as well as gate of the door, what would you do? You'd be able to go inside. So the gate, the key of the gate and the key of the door will get you inside. So that's the word "and" coming in between, and hence this is how the NAND, and hence this is how the AND logic gate has this specific truth table. And in the case of OR, let's look at how we reach the OR. Imagine this is the same house. We're going to ignore the gate key, all right? And Y is getting inside the house, but C, D are two sets of keys, okay? C and D are two keys. Now let's look at it this way. C and a D with the Y. Imagine you don't have both the keys. Would you be able to go inside? Obviously, no. And one fine day, you happen to have the key of the D. Will you be able to go inside? Yes, you can. With the key of the C? Yes, you can. But what will happen if you have both the keys? You could use any of it and go inside. Isn't that true? And hence, this is the truth table of the OR gate. So we're going to go and do that here. C and D is Y. Once again, when you have no keys, you will not be able to go inside. When you have one key, you will be. Another, yes, you will be. And the last one, when you have both the keys, obviously you could use any one of it and go. All right. And the last one is the NOT gate. NOT gate is exactly to do the opposite of what is given. That is, there are some times where you feel like it's raining and it's not supposed to go outside. If you have this urge that, okay, I'll just go outside because I was told not to do it, right? That's exactly the working of the NOT gate. It is kind of the naughty one. Okay, so if there was no input, this guy would be giving us an output. But if there is an input, he'll make it to the opposite. As simple as that. Now, these three are the basic gates and with which we can define these plays. Okay, so NAND, as I told you, is not AND. So we'll just look at these two truth tables. We have not AND and NOT. I'm just going to draw it. F and G. I'm not going to draw the W yet, okay? Yeah, I'm just going to draw it after a gap. This is just my working space, so there's no specific name for it. Now, if it were to be an AND gate, you can see that it will be a 3 zeros and 1. So I'm just going to draw the 3 zeros and 1. Now, this is AND. Next part is a NOT AND. This 3 zeros and 1s are going into this NOT gate. Okay, so when the 0 goes into the NOT gate, it will be turned into a 1. Similarly, this is going to the NOT gate, it becomes a 1. And this one, yes, this one as well becomes 1. And when it is a 1, you can see if I give a 1 to a NOT gate, it becomes 0. I know this could be a little bit confusing, like why are we using 2 gates and why not this after this or this after this? Why are we confusing that? The NOT gate can only take one input, remember that. And we're going to draw, remember drawing AND gate like this, like you have A and B out here, this Z is coming out here, this Z is going here and getting converted into the W. This is what is happening here. Now that's why the NOT gate is not before the AND gate. We are giving two inputs and we want only one output. And in simple terms, the opposite of the AND gate, FG as the AND, and whatever you think comes out of the AND gate, you just have to reverse it. Like the key of the gate is here, alright, and the key of the door is here. Obviously they will not be able to go inside in these first three cases. In the last case, when they have both the keys, you'd be able to go inside the house. That was the condition for our AND gate, right? And here what happens is you just reverse the output. So if you write this as the NAND's output, you won't get any marks. So this is just to be in your mind, okay? So in case if you're going to write it there, I mean, you're not getting marks because it's wrong. This is the truth table for the AND gate. For the NAND, you obviously have to use this same method. Alright, so that's your NAND gate. Now let's look at the NOR gate. We have mentioned this as not OR. So H, I, and the output is the V. So imagine that it were to be a OR gate. In an OR gate, you know that any one input is enough to give an output. So I'm just going to draw roughly what happens if it was an OR gate. This was for an, when the output of an OR gate passes through a NOT gate, you just have to change the 0 to 1 and the 1 to 0, right? This is a rough working space and this is the output of the NOR gate. Now let's look at the XOR. The exclusive OR. This is the condition similar to the OR gate. We have J, K and U here. So from this kind of input condition, we just have to exclusivate the output. Previously we had the OR gate output C. As I told you, when both the keys were not there, this two keys for the same doors in a row, right? So both keys are not there, you would not be able to go inside. When any of the keys is there, yes, yes. But when you have both the keys, you'd use any of it. In exclusive OR, that is the only definition separates it from the normal OR gate. Like when you have both the options, it's kind of like a jealousy or a possessiveness happens between these two, and then it keeps fighting between these two and you don't go inside. So only when one of the keys is there, you'll be able to go inside. That's exclusive OR. Yeah, it's also called as X or EX. It is called as EXOR, so that people pronounce it as XOR. And even if you write it like this, there is a tendency to go to XOR, but it's not XOR. It has to be exclusive OR for you to remember how it's working, because we'll be discussing a lot of questions on these 6 gates and different combinations of these 6 gates. Very critical to know each gate by just the word. So to summarize our lesson today, we learned the 6 different logic gates and the symbols of AND, OR, NOT, NAND, NOR and XOR, and we tried to fill up the